We can start now.
Okay.
Yeah.
Good morning or good afternoon, everybody. I think I'll start then, or yes,
Just
or
1 minute, Pratyush. Just let me introduce. Uh,
okay.
Good afternoon, good morning, good evening, everybody. It's the fourth chapter and fourth session of Praktani Adda, a concept created by Vidyapit Praktani, the Alumni Association of Ramakrishna Mission Vidyapit Deoghar. In context of the ambition, plan, and thought process we all have at Vidyapit Praktani, this fourth episode is still in a very early phase, and in spite of that, we are, I will say, heavily encouraged by so many intentions, so many eagerness for participation. After investment, COVID vaccine session, and one more, now we have cosmology, something which is, or I will say, which intrigues lot many, but understood by very less, including me in this bracket. But here we have one more talent from Vidyapit Production House, Pratyush. I am sure everybody will enjoy the session, and throughout the session, while enjoying, as I do, I keep on thinking about the amount of effort and enthusiasm put in by Ritesh. That is the beauty of Vidyapit. And at Vidyapit Praktani, we intend to showcase the talent pool we have, and in turn get the bonding, enlarge our horizon, and slowly and steadily build up to build a better, inclusive, and bigger Praktani. I, on behalf of Vidyapit Praktani, welcome all the audience who have been part and parcel of Vidyapit Deoghar at some point of time to join us and build this fraternity so that we can really deliver in terms of some tangible and intangible benefits as a alumni association. Thank you, everybody. Over to Pratyush.
Thank you, sir. Good afternoon, good morning, and good evening, everybody in that sequence. And thank you, Ritesh and the Alumni Association, Praktani Association, for allowing me and inviting me to present something on cosmology, the subject that I work on. The topic of the talk today will be conscious universe, cosmology, and Big Bang. Though on second thoughts, I decided to keep the conscious universe part of it on the later side of the talk, chiefly because I'm not the expert on consciousness, but because we studied at RKM and with Vidyapit, we are very much on some level engaged with these thoughts, at least, and not only us, all of humanity on some level is engaged on these thoughts about what are we, why are we here, what are we doing here. So I'll give you a scientific perspective on what we understand about the current state of the art of what the universe is, what the contents of the universe are. So we will ask some questions in the process of what the contents of the universe are, for example, and does it have a beginning? Will it end? And questions like these. Broadly, so cosmology is questions that concern our origin and our fate. Where did we come from? Why are we here? Is our existence a fluke, or is this a natural outcome of some physical processes? Should we expect more of us like us around in this universe, or like what is our state here? And chiefly it's from a human-centric perspective, of course, but we also like to understand like the general mechanisms of how the place that we exist in operates, more or less. And so this picture that I show you here, this represents our current understanding of This is a summary of our current understanding of what has happened in the evolutionary timeline of the universe. So if we understand correct, like there is a phase, that there is a point where the universe is created. This is the current standard model of cosmology, the Big Bang model. We will go into it, what are the shortcomings of this model also, and what are the unanswered questions, and what may be improvements, what could be different. So if Big Bang happened, there is a moment at Big Bang, then there is a short burst of a phase called inflation, which lasts a very short period of time. Then around about 375,000 years after Big Bang is when we see the first light that appears in the universe. This is the cosmic microwave background. We will talk about all of these things in phases. After that, you have a period when there is nothing happening. There is no light in those ages at that time. Then at some point, there is again activity starting in the universe. There is star formation, there is galaxies coming up, and then there is evolution of the universe. And right about around this time, we also understand that the universe is expanding. But around recently, what we also figure out that the universe is not only expanding, it's also the expansion is accelerated. It's expanding faster and faster as time proceeds. With a caveat, if I not only this also becomes a little bit political at this moment. When I say that the universe is expanding, all of these things, we have to remember this is based on certain models of the universe. There is always a base model that we think things are working like this. And if things are working like this, at least in the case of the universe, where you do not have a direct observation, you cannot go at the moment of Big Bang, at the moment at least, to confirm whether there is a Big Bang or not. So we can only make indirect observations and inferences from our observations, or theoretically also, and then you can make a prediction. If my theory is correct, you will see something like that happening over there. So at the moment, the standard model of cosmology is Big Bang. We will also go into why Big Bang became Big Bang. How did it get accepted as Big Bang? What happened before Big Bang? All of that, we will go into it slowly. But if that's the case, then what we understand of the universe at the moment, if the Big Bang model is correct, what we put the numbers in, how we put these models, then we see that the universe is expanding and the expansion is accelerated. And this is at the current moment. But this all, if you change the basic model, it's quite possible that something changes. Then you don't see some, but we will go into all of these things. So the basic underpinning of saying this is that there is a statement called cosmology is religion. And a few years back, I did not understand what that meant. But quite a few things are beyond the reach of verification, observation, proof. And then it depends on how many people believe it. Much like religion, it depends on whether, like, if majority of the population believes there is no God, all religious institutions die down. So if majority of population does not believe there is Big Bang, it will die down. But science goes in a little bit of a different way. Before it disproves Big Bang, it has to have a very concrete proof. It will, like, it's a very lethargic process. It will not give up the standard model so fast. But anyway, these are the problems that we talk about. And this is the map of the expansion and the beginning, the evolution of the universe. And if we understand that Big Bang is correct, then we are roughly 13.7 billion years old, and the first star started forming around 400 million years old. And this is the phase of our development till now. And how do we understand all of this? Like, there are most of the times we give a theory, and then to verify that theory, we need some observations. And those observations sort of indicate if there is a prediction that if there is a theory correct, then you must see something. Like, for example, when Einstein gave his theory of relativity, it's a very esoteric theory. Does it stand correct or not? Then the theory should predict something. One of the things that Einstein's theory talks about is that there is a curvature in space-time. And if there is curvature in space-time, and if light likes to move through the fastest possible path, which is called the null geodesic, basically, then you should expect that light should curve around very massive objects. This was one of the predictions of Einstein's theory of relativity. And immediately they noticed around, like they put up a telescope to sun at some point during solar eclipse, and they noticed that there is a bending of light happening. And that was one of the first proofs of Einstein's theory of relativity. So it's not like you give a theory and it should be accepted immediately. There should be some predictions that can be verified. And one of the predictions that actually clinched the debate in favor of Big Bang was the observation of something called the cosmic microwave background. And the picture that you see here is the full sky picture of the cosmic microwave background. Recently, there was a satellite called the Planck satellite that went around 2009, and then it made this temperature map of the early universe. This picture that you see is roughly 13 billion years old, meaning around about 300,000 years, 370,000 years after Big Bang. And this picture that you see now, it's very detailed. In the beginning, there were previous satellites who do not give such detailed pictures. This is an evidence of how big, and that clinches the debate in favor of Big Bang. Why? We will talk about this later. And this is a detailed picture of the cosmic microwave background. All the regions that you see in blue are regions which had less matter density, for example. All the regions that you see in red here are the regions which had more matter density. The cosmic microwave background, this is a picture of light, but that light at that time, like CMB, so we will use the acronym called CMB. This is the map of the light at the moment when light separated from matter for the first time in the universe. So the distribution of matter also is imprinted in this picture of light that we see here. And so if we study this light distribution map, we have a knowledge of what was the matter distribution in the early universe. So these are the indirect sort of investigations we take to understand the mechanisms of the universe. And if this picture that we see right now, this picture has a lot of information that you cannot see in the naked eye. But if you did some sort of a data analysis, if we looked into, I'm not sure if like how many of us, at least some of us are aware of what is a Fourier transform. If we are not, we are at least aware of, let's say you are in a three-dimensional space, then you need three independent coordinates to move in three directions. These are called the dimensions. Similarly, you can have any signal and you can decompose those signals in terms of some independent signal basis functions. And here you see the cosmic microwave background light signal in the sky decomposed into some sort of frequency basis. And these ripples that you see, there are these multiple peaks in the frequency spectrum of cosmic microwave background. This actually tells you what is the content of the matter content of the universe. What is the energy content of the universe? The ratio of the first peak to the ratio of the 0th peak. It tells you about the expansion, what is the expansion rate, something like that. But these are all very detailed models of the thing. And we can look at the fluctuations of light in the cosmic microwave background, and we can get a hint about what is the energy content, the matter content of the universe, things like that. So over the past few years now, we have entered the age of precision cosmology. But with all of this, we have to remember the caveat that assuming that the model that we think of the universe that is correct right now, which is the Big Bang model and something called the Friedmann Robertson Lemaitre model, which comes out after solving the Einstein's equation for general relativity. If those are correct, then these are the things that we know about the universe currently, and we can measure it to such precision, meaning that the age of the universe is roughly around 13.7 gigayears or billion years. The space is expanding at the rate of 67.7 kilometers per second per megaparsec. What this means is that if I'm standing here as an observer, if I go 1 megaparsec away, a parsec, by the way, we should define what a parsec is. Parsec is an astronomical unit of measuring distances. It is about 3.26 light years, not about, this is around, yes, this is around 3.26 light years. And a light year is what light travels in 1 year, the distance. So 3.26 light year is called a parsec. A megaparsec is 10 to the power 6 parsecs. You should think about the magnitude of distances that we are talking about here. But because the universe is very huge, all this, so we have to like change our definition of scales a little bit. Here, the universe, what we understand today, that the universe is expanding as we go 1 megaparsec away from here at our current position. The rate of expansion has increased by 67.74 kilometers. Next megaparsec per second, like, yeah, it's so as we go farther and farther, the rate of expansion is increasing more and more. And then what we understand is that the average energy density of the universe is around 0.8, 10 to the power minus 29 gram per centimeter cube. The horizon of the visible universe is around 41 gigalight years. There are around 100 billion galaxies in about our visible universe. There are 200 into 10 to the power 18 stars, something like. So these are the numbers that we get from the precision cosmology moment. There is also another thing that we will go into it later, that space is almost perfectly flat, which is that the curvature is almost zero. What this means, in 2 dimensions, it's much more easy to see. Let me just 1 second. If you have a flat space, meaning if we look in 2 dimensions, the sheet of paper is a flat thing. But if we curved it like this, then it has a positive curvature. If we curved it like this, it has a negative curvature. And all of this is the geometry of space. This geometry of space, something like this can happen in 3 dimensions as well. And this actually determines quite a lot of the evolution and what is going to happen in the universe, the matter content and the geometry. So this thing that we measure, that space is almost perfectly flat, it has a big implication for what is the history and the future of the universe. And we also understand something, which is something called that we don't understand a lot, which is these last 3 components. Here you see there is something called dark. There are 2 names here. We see baryons, dark matter, and dark energy. This is called dark for a reason. There is a reason behind this name dark, meaning that we don't really know what this is. If we look at the energy content, if we understand what the model is correct, and then we look at what the energy contents are, the things that make up the visible universe, meaning you, me, the stars, the galaxies, everything that we can see, that only accounts for around 4.9 or 5% of the energy content of the universe. Around 26% is something called dark matter. We don't know what it is, but we know it exists because it influences the behavior of visible matter. Like it acts gravitationally, it has a gravitational impact. Now there can be another thing. So if there can be 2 interpretations to this. Either what we understand, our theory of gravity is wrong, or there is an exotic sort of matter which only interacts gravitationally and not electromagnetically. So it does not interact with light, we cannot see it, but we feel its presence because it affects things gravitationally. The first time dark matter was actually, since we all studied physics, it would be easy to understand this, that for rotating objects, if it's a solid object, the speed of rotation is the same, like it should have the same thing. But the angular velocity is the same, but the radius goes away. So like this is constant, but when an object it's not solid, then it should have the, we know the rotational velocity of an object when we look at it, and this is related to the mass it contains. So when people looked at the galaxies and they tried to look at, you can imagine the situation as cherries on top of a cake. Only cherries are visible, that underground cake is not visible. This is the dark matter that we are talking about. And now imagine if you started looking at the velocity of the cherries on the cake. So everything, if we know gravitational theory, that mass affects for rotational objects, all the matter contained inside the the sphere that bounds that object that influences its rotational velocity. Then you can, if you observe the velocity, you can infer the mass. And when they looked at the galactic rotational velocities, they noticed that the visible amount of matter was not sufficient to account for the rotational curves that they saw with the galactic rotation of objects. So there is something going on that we don't see, but it affects things gravitationally. And then there is something called dark energy, which is around 68, 67% of the whole universe, which is dark matter. At least we know that it's expanding thing, like it has a gravitational impact. Dark energy, we don't understand at all, because this is apparently responsible for the accelerated expansion of the universe. We see that the universe is expanding. It is expanding accelerated. It has mass, it has matter. This is where the ultimate form, the curvature of the space-time comes into play itself, because matter itself, given it is only gravitationally attractive. So things have a tendency, if there is only matter, things have a tendency to clump together. But what we notice in the universe is that things are expanding and expanding away from us. So there is some force that's counteracting the force of gravity. And as time is passing, this force is becoming stronger and stronger. And we don't understand why. This is one of the, so there is something naturally missing. This is a time of we live in a time cosmologically when actually this is interesting scientifically, at least, because a lot of things that we see, we don't understand, meaning there is something missing in our understanding of the universe, at least, what our current models are giving. And these questions, they are occupying us since the start of the time, I would say, which are roughly, we can ask questions like, where does the world come from? What is it made of? How did it begin? When did it begin? Did it begin at all? How big is the world? And what is our role in understanding? What is our role in the cosmos? And what is the eventual fate of the universe? In the next few slides, we will look into some of these questions and try to see what we understand and know about these questions. So first of the question that we ask is, what is the size of the universe? Is it infinite? Is it finite? What is the, well, we can ask question, is it bounded? Is it unbounded? We have to remember that now we are going to the depths of our knowledge, in the sense that we know that there is something called speed of light, at least if general relativity is correct. And what we understand from classical physics, the upper cap on the propagation of speed, the information, is the speed of light. So eventually, if the universe is big enough and it's expanding faster and faster, you can imagine that there is a region in space whose light has not reached us, and it's also receding far away. So there is, in future also, its light will never reach us. And eventually, like, there are regions in our space which are continuously going out of our horizon. And so we do not know. Can we even infer these questions? Can we know the answers to this question? Is that from the finite, can we ask about the infinite? Like, these are the questions about the size and boundary that we can ask. Next, we can ask the question is, which is actually the most important thing from our perspective, because in the end, this is the anthropomorphic perspective that we are interested in, because we are the only observer that we are at least aware of. What is our place in the universe, and what is our role specifically? Why are we here? And why is the universe so fine-tuned? This fine-tuning, there is something called the fine-tuning problem, meaning we can ask the question about why are certain, like, most of the parameters, why are certain constants, most of the constants in the universe, they have the values that they have. Meaning, we could ask, there is something called a fine structure constant. It determines the balance between the force of the force between hydrogen atoms splitting the various energy levels. There are a few other things, and if these numbers were a little bit more or less than from what they are, these atoms will not form. If these atoms don't form, the higher atoms don't form. If higher atoms don't form, molecules don't form. Eventually, at the end of this train of thought, we don't form. So if, like, some of these numbers, some of these constants that we are aware of, if they had different values, we would not be here to ask this question, why we are here. So this is called the fine-tuning problem versus the anthropomorphological problem. Is that why are certain numbers in the universe exactly the way they are, that it evolves into us eventually? We should remember that we are part of this universe. That if we are asking this question, this is a very famous saying by Carl Sagan, that us asking the question is in a way the universe itself asking itself questions. Like we somehow have evolved, this whole matter distribution over some period of time has evolved into us asking these questions. So why are these things just exactly the way they are, that we can form to ask these questions? More questions that we can ask is that why are the physical laws the way they are? Do they need to be like this? Can there be different set of physical laws? How many dimensions does the universe have? Is it the space like 3 dimension and time like 1 dimension that we see? Is time even a dimension? But we will not go into that, the whether time is a dimension or not. And then what is the origin and fate of the universe? Does the universe have an origin? If it does, how old is it? How do we know that the universe has an origin? Did it always exist? If yes, then is it infinitely old? These questions. And then if there is an origin, is there an end to the universe as well? The next questions that we can ask is, what is the content of the universe? What are the components? What is it made of? How does each of the components influence the evolution course of the history and the evolution of the universe? And how each of these components by in turn is influenced by the structure of the universe itself. And then in the end, we can also ask, is our universe unique, or are there many other universes like our universes? And what made the universe originate? What is the reason it came into existence? And the last question is that, are our brains also one of the very important questions that we have to always ask? Is our brain equipped to answer the questions that we are asking? And is our brain even equipped to ask the right questions? So these are the questions that we can ask, and some of these questions we will go into this in this lecture for a little bit, depending on how much time permits and how far we can go. And each of these questions we will go step by step into in the next few slides. So how big is the universe? As far as we understand right now, like if you think about it, today we know that there are galaxies which are out of our galaxy. There is something beyond solar system. There was a time when we looked at the night sky and we thought these are jewels studded in the sky, and like there is a dome and nothing is moving. So it's what our understanding of the universe right now, about that there are galaxies which are larger than our galaxies, and that the universe, the content, the size of the universe is so and so giga years, light years. This is like really huge numbers. If you think about it, this is not very natural because this is not visible in the sky. How do you find this? So these are all, this is a series of successive steps that humankind has taken over a period of centuries, millennia, that has established our current understanding, which still, of course, lacks a lot of things because we are not that powerful. But anyway, to end the question of size of the universe, the picture that I show here, this tiny inconspicuous dot that you see here, it's one of, if not the most important single object in the history of cosmology. It is one of the most important single objects in the history of cosmology. This is a star which we called M31V1. M31 is the name of the galaxy Andromeda. And even the question that we have a galaxy which is our neighborhood galaxy, this was not always known, but we now know it, that there is a neighborhood galaxy. And the star is called V1, so M31V1. This is a special star because this star has its luminosity over a period. This fluctuates, and there is a standard relation in its fluctuation over the luminosity period relation. It has a very standard luminosity period relationship. Now, why this is important, there is a concept called standard candles. If you know there is something called an intrinsic brightness of an object. If you know how bright an object is intrinsically, then you also know how far, like from its apparent brightness, you can deduce how far it is. because we know how bright it is supposed to be. We know how light dims, how it goes away from us. So we know if there is like, if we have seen an object whose intrinsic brightness we are aware of, then we also can calculate its distance. This is how we build up how we understand distances in astronomy. Like if we measure the distance to a successive galaxy, to our neighborhood galaxy, it's actually not a very easy process. To understand this, we have to understand the concept of distance ladders and distance scales. The concept is something similar to what you see in the picture here. All these street lights, these are halogen sodium lamps. They give out light at a certain fixed wattage. If you know that wattage, then you see as it goes far away, it gets dimmer and dimmer. So how far away it is. And in the process of, so we have certain standard candles also in astronomy that are used to determine the distances of objects. During like one of these standard candles is something called a type 1a supernova. Like somebody asked me questions about, there was a question that came, what are supernova and what do we know about them and how is black hole? So this is another topic altogether, the life cycle, the stellar life cycle. But one of the things about some of the supernova is that we know that they burn at exactly the same moments, meaning when they attain type 1a supernova is actually a star in the white dwarf in the companion of another binary star from which it is stealing its matter. A white dwarf is a very massive object. It is in presence of another star and is stealing the star from the gas from this other star. When this white dwarf reaches the mass of 1.4 times the mass of our sun, it goes boom, it goes into explosion. Because we know exactly the mass when it goes into explosion, we know its intrinsic brightness. Then if we know, like if we determined, we saw a type 1a supernova, we also know what is the spectrum, what is the light spectrum of, like there is a characteristic light spectrum. Then you know what is its brightness, you observe the brightness, you determine what's its distance. But to get, so these are examples of standard candles. There is also something called the standard ruler in cosmology. This is something akin to fixing the size of horizon of what light could be at different times in the time scale of the universe. So one of the standard candles is what I said is a type 1 supernova. The other standard candle is something called a pulsating star. There are two kinds. One is just one second. I have to remove this on this side here. So there are a few different kinds of star. One interesting kind of star is called a Cepheid variable star. This is what the M31V1 star is. This changes its luminosity over a period of time, and we know what is the luminosity relationship. And Andromeda M31V1, this is the star that helped Edwin Hubble to determine the distance, like the rate of expansion of the universe. Because this is also a standard candle. So once we know its intrinsic luminosity, we also know what the distance of this object is. If we find this object is in. So if we find this object, let's say when we found this star M31V1, we were probably not, I'm not really sure. This is a part that I am not 100% sure about, but we were not aware of something which is beyond our galaxy. Actually, we were aware of our galaxy's existence, but we were not aware that there are other galaxies. So when he observed this star, the distances that we calculated, this came out to be much larger than the size of our galaxy. So then we had to change our notion that, oh, there may be other objects in the universe which are not, and because this is a star, so there must be a containing object. And slowly they did all of these things and they realized that, okay, there are more objects in the galaxy than our own, in the universe than our own galaxy only. And the lady who is credited with discovering this star is Henrietta Leavitt, and this is the periodic luminosity relationship of the Cepheid variable stars. And this is a well-known phenomenon. So if you know the period luminosity, you know how its luminosity varies over a period of time, then you observe this object, and you also know its intrinsic luminosity because of it. Then you know how far these objects are. And this was one of the first discovered Cepheid variable things which was in the other galaxy. And This is the original deduction of Hubble. Edwin Hubble is the scientist who was credited with finally confirming the expansion of the universe. Before that, there was the theory that the universe is steady and not really expanding. There are many things, we will go into it slowly in details in the next few slides. But the fact that we understand that the universe is expanding today was not always common knowledge. Same as the fact that Big Bang is a common knowledge, it was not a common knowledge. There was, before Big Bang, there was a theory called the steady state theory. And how Big Bang got clinched into being the forerunner for the most accepted theory, this we will come into all of these things in a little bit later. The next question that we can ask is, what is our place in the universe? For this, I show you some pictures of the Cassini spacecraft that visited the Saturn. I think we are all very aware of this phrase called the pale blue dot. This originated from the pictures that Cassini spacecraft took from close to Saturn. And here in this picture, you see, this is Saturn, and you don't see Earth, you don't see Mars, you don't see Venus, but they are there. This is our size. This is the pale blue dot we are talking about. Once we enlarge the picture, this is the picture of Earth from the vantage point of Cassini when it was close to Saturn. And this is how big we are in the scheme of things when we think we are very big. These are the pictures, real life pictures from Cassini when it was close to Saturn. So now we go next to what the way we talk a little bit about what is the content of the universe. But before that, we also talk a little bit about one of the very defining theories of our century and also the last century of this millennia, last millennia. This is the Einstein's metric theory of gravity. Before Einstein, it was the accepted theory of gravity was Newton's theory of gravity, where matter was decoupled from space-time, meaning that matter existed independently and space-time was flat. There was no action of space-time on the movement of matter and the other way around. Einstein came and he says, no, there is something else happening, meaning that space-time and matter, they are coupled, and how matter is influencing how space-time curves, and in turn, the curvature of space-time, it influences how matter behaves. Newton, this is the thesis of Isaac Newton, I think, apparently, and no, this is Principia Mathematica Naturalis. This is where he published all his results in the beginning. So in the Newtonian view of cosmology and our understanding of gravity, actually, by the way, maybe this would be surprising to you that we are aware of 4 forces of nature. We talk about gravity the most, we feel it the most, but you would think that we understand a lot about gravity, but this is actually one of the least well understood forces of nature. There is Newton's law, there is Einstein's law, we understand, but there are still discrepancies in our observation. On the other hand, the strong nuclear force, the 4 forces in nature that we are aware of, these are the strong nuclear force, the weak nuclear force, the electromagnetic force, and the force of gravity. The rest 3 of them we understand pretty well, but the gravitational force, we have doubts, because we cannot, for example, we cannot conciliate the theory of gravity at very large macroscopic scale. Macroscopic here also means a grain of sand. That's already very macroscopic. And also at very small scales, that's quantum, at the scale of atoms and things. Like, also consequently, we do not understand black holes very well, because black holes are supposed to be, from what we understand, this is massive object. This is a very massive object which is concentrated at a pinpoint. This is where laws of gravity, they break down, because if you understand, law of gravity says it's 1/r law in general, it comes as. But at the point when r is 0, it is infinity, and so we don't have a way of explaining what it is. Then we expect maybe there would be some sort of a quantum law of gravity and quantum theory of gravity. But then they should match the quantum and the classical theory of gravity, they should match. So this is a big problem. We don't understand it very well. But in any case, so all this is happening at the moment. These are the current evolution on state of the art regarding our understanding of the gravitational theories. before Einstein started, we used to think that the universe and the time is absolute and it's uniform, and space and time are independent of matter. And about dynamics, we understood that the action at a distance, it is instantaneous, and it was edgeless, centerless, and infinite. And there is also something called the cosmological principle on which we base all our theories, namely that the universe looks the same at every, so no observer is different from any other observer, everywhere in the space is the same. And so this results in an absolute static and infinite space. But then Einstein's universe, it says that space-time is dynamic, meaning that it curves and it tells matter how to move, and the curvature is determined by the mass. So these objects, they are intertwined with each other. How much time do we have, by the way? Riteshda? Hello?
We have 15 minutes around.
We only have 15 minutes right now, is
We
it?
can extend it to 5 minutes more, so 20 minutes, please.
Okay, then I will go a little bit faster then. So, okay, Einstein's universe. This is like, so Einstein's universe says that the local curvature, it's determined by mass and how things curve. And then
Pratyush, I would just interrupt. So you can continue till 2:15 for half an hour more, and then we have 15 minutes of Q&A. So we wrap up by 2:30 sharp.
okay, I have half an hour more, you say.
Yes, you can.
Okay. Fine, sounds good. Okay.
Thank
So that's around, okay, fair enough. Sounds good. Okay, then I keep a track of my own time here also as well. Thanks. Okay. So Einstein universe says that space-time is dynamic and matter influences how space-time curves, and space-time tells matter how to move. And this is the famous equation. It is very simple looking, but this is very complicated to solve in general if you do not make some assumptions. And then we can ask the question, what is our fate? And on this question, we go into define the questions that we have been, the thing that we have been talking about, the expansion of the universe. I'm building up to a story about how Big Bang also like got clinched as an evidence. So we are aware of something called Doppler's effect. When sound or light, when something moves towards us, its frequency gets smaller, like the frequency is compressed. And as it goes away from us, its frequency enlarges, it becomes larger and smaller and smaller. Frequency wavelength is larger, there is an inverse relationship. Something similar happens with light. When an object is going away from us, its light shifts towards larger wavelength and it looks more red. When it is moving close to us, it is blue shifted. So when we looked at objects, so now you can imagine when we look at all the supernova, everything, we see a light curve, which is characteristic of the supernova. But the whole light spectrum has shifted more in the direction of the red. And from this is also one of the reasons when we understood that the universe is actually expanding. So the first indications of cosmic expansion was by these guys in Sweden, that they looked at the radial velocity of 44 galaxies, and they saw that there is a relationship between a redshift of we can measure the redshift of an object. We can see what are the spectrum, how the light is shifted. And then in the distance, and they saw that there is this graph. This is all data analysis. This is the second part of the talk. Like these are independent points, and how to find is there a pattern in these points? Is there like people who are doing data analysis, they will be familiar that maybe we can do a line of regression here and see if there is a linear relationship or something. But it is not so clear in this picture that there could be a linear relationship. So and this distance and redshift is an indication of things shifting away from you. Redshifted objects mean that things are moving away. And as more redshifted, so there would be a relation. If you see an indication that as you are further away, things are more redshifted, this would be an indication directly that the universe is expanding. Why? Because we know that like things are redshifted if they are moving away from us. That's a motion. And then if they are more redshifted away, if a standard candle, if we detected a standard candle across various galaxies in the universe, and we noticed that there is a relation there, because we remember that it has to be, its intrinsic brightness has to be the same. And then its intrinsic properties are the same. And then if we notice a pattern that there are it is redshifted with a distance, then we know that the universe is expanding faster, faster. So around 1927, the second indication came from this guy called Georges Lemaitre, who's actually a very important guy. He is the creator of the Big Bang theory, basically. And he, interestingly, was a priest in a Belgian church, much like our Biman Maharaj, who was a very, if I don't know if you know about Biman Maharaj. He is a mathematician at RKM in Belur and the college over there. And he is a first-class mathematician. He is a hardcore scientist. He's a very strong mathematician. And he has got like medals from a lot of places. He's well known over. Similarly, this guy, Georges Lemaitre, he is a priest in a Belgian church, but a very strong mathematician. And he solves Einstein's equations, given all of these things, and he comes to a conclusion that because the universe is expanding, and then it should have a, either if you see there is an expanding evidence, and then you solve an equation and you see a motion, then expanding things you can retrace back in time, and you can say that there is an origin if there is this motion happening. But the problem with Georges Lemaitre was he was a priest in a Belgian church, and church is very much obsessed with the myth or the fact of creationism in general, God and science, like God is the creator. So when this dude, when he is coming from a church saying that there is a moment of creation of this universe, the mainstream scientists, they laugh at him. There was a BBC radio interview by a very big famous scientist called Fred Hoyle in 1944. He's sitting on BBC interview, BBC. So somebody asks him, and the interviewer asks him, he said, hey, there is this priest in Belgian church, he is talking about this and the start of the universe. The paper is called The Primeval Atom. That's the paper that Georges Lemaitre wrote. And then Fred Hoyle, he laughs, oh, this guy talking about Big Bang. This name Big Bang started as a joke on BBC radio, and it was a derisive term. Georges Lemaitre dies. He gave his theory. He wrote this paper in 1933, and he dies around the end of World War or something. And he dies in ignominy because everybody was laughing at him. 2-3 factors that happened, because one, he was a church priest. So they thought this was church's propaganda for creationism. But around 1967, we will come into this, like he got vindicated eventually. And Big Bang, well, he got vindicated. He is the original proponent of Big Bang theory. We do not know about it, but the fact that we know that Big Bang, we accept Big Bang as a theory right now, is a vindication of this guy. So, but finally, the expansion of the universe, it was by Edwin Hubble. He saw this graph, he found a redshift linear distance relationship, and he concluded that the universe must be expanding. And this was, yeah, he actually, no, he did not conclude, in fact. He saw he saw there is a linear relationship, which is this, as you go far away, the things are more redshifted. But he himself did not understand that this was the conclusion. This was something in favor of an expanding universe. Einstein himself was also not in favor of an expanding universe. Maybe you have heard of this thing that there was, Einstein made the biggest error of Einstein, the cosmological constant, the blunder of Einstein, all these things. Because if you think about it, now that we say that, okay, that the universe is expanding, but it is not very natural to see this, because when you look at the night sky, the stars, they are not really changing. You don't see anything to the naked eye. So to come to this conclusion that the universe is expanding, it had to overthrow some set notions. And the set notion was that the universe has no beginning, no end. It is a steady state, in a steady state. It's not ever, never changing. And so somebody comes in between and says, no, it has a beginning. That's a big problem. And if that guy is coming from a church priest, then it's even a bigger problem. So all of these things, these were problems till then. But Hubble discovered the expansion of the universe. This is the original Hubble plate, actually. You see, like if you look at things over a period, this is the plate. Each of these circles is a galaxy. And if you do again an exposure on the same plate, after keep exposing again after a period of time, you will see that these things, here is the center, and these are the same things. They are expanding. They have changed their place. They move away. So all of these things, they were indication that the universe is expanding. And our modern understanding of the expansion of universe comes through supernova, actually. These are the standard candles that we talk about. And one of the most important supernova in the history, recorded history, is the supernova called SN1006. It was actually seen in the year 1000 AD, something like that. It is the brightest recorded supernova in the history of the humanity, the written history of humanity at least. And its peak, it was brighter than the crescent moon and much brighter than many other objects in the sky. So how we understand the universe is expanding, we track supernova basically, and specifically type 1a type supernova, whose intrinsic brightness we know about. And we look at galaxies. We are actually looking for supernova events. We point our telescopes in the universe and we look at pictures and we look for evidences of supernova in distant galaxies. And we measure their redshift, we know their distance, and then we can look at the expansion and the map of the universe. For example, in a picture like this. On January 15, you don't see anything around here, but July 7, there is a big spot in the middle, which is a supernova. Another picture around here, like things go off quite a lot explosion in the universe. So now remember, we are asking the question about what is our fate? If the universe is expanding, then we had a past, we had a beginning, but we can also ask the question, what is our fate? What is the end product that's going to come up? And this again, of course, is all model dependent. If we understand what is the content of the universe, then we know its expansion. Then we can ask the question whether things will come down. This is where curvature also comes in. So now we have to remember, we understand that the universe is expanding, but the matter is supposed to be contracting. Gravity is an attractive force. There is something called dark energy that is making the universe expand. Then the question eventually is the strength of these things, which is stronger and which is weaker. Eventually, if dark energy turns out to be stronger than than gravity, which we see with the accelerated expansion of the universe, then everything will eventually be ripped apart. If the curvature of the universe were to be negative, then it also implies an expanding universe, and everything would be ripped apart. But if the gravity somehow won over this disruptive, dissipative force, then everything would eventually come together in a crunch, or if things are exactly balanced, then the universe will be going on how it is going at the moment. But all of this, like we will see eventually that our horizon also will change. Here is a schematic. Like your observable region of the universe is determined by the yellow, for example. In an expanding universe, your observable horizon will also expand, but the background universe is expanding faster and faster also. So it's quite possible, even though your horizon is expanding, things are going still beyond your horizon because the universe is expanding faster than the speed of light beyond some point. So at some point, eventually, we will not have anything. And then, so if what we understand from today, if the general cosmology is correct, if our understanding, if all this, the equations that we derive from Einstein's theory, using the most simple general assumptions, if we understand that the space-time, our energy matter content of the space-time is correct, given modulo all of these factors, we have a rough idea of what will happen in the next 100 giga years, around 5 billion years from now. Look, this is on if you see this picture on the top left corner is what is roughly, this is an artistic impression of what is going to be happening in the universe in the future and what's right now. In the topmost left picture, this is our current field. We see the band of the Milky Way, and also this is a few nearby galaxies. But around 5 billion years from now, our sun would have turned into a red giant star. And I don't know how many of you know right now, but we are on a collision course with Andromeda galaxy, which is our nearest galaxy. We are moving towards each other at a speed of around 660 kilometers per second. And it will take around 5 billion years still for this collision to happen. So you can imagine how far and how big things are. But around 5 billion years from now, Andromeda galaxy will be on our horizon. And about imminently to be collided. About 100 billion years from now, the collision of Milky Way and Andromeda has completed, and what's remaining is a fuzzy. Right now, our galaxy is a spiral galaxy, but after this collision, things will relax and it will become a more fuzzy, spherical ball-like galaxy. About 100 trillion years from now, if what like our expansion of the universe is correct, what we understand, most of the objects would have died out. That's the final light out. If modulo what we understand is correct, the last of the stars would have burned out and everything has gone out of our horizon, and that's the final light out. This is around 100 trillion light years from now on. So we don't need to worry about it so much right now. Plus, maybe our understanding is not totally complete also. One more question that we can ask is, what is the energy? What is the content of the universe? This is the latest understanding, what we understand from our experiments. What is the latest content of the universe? Out of which around dark sector, things that we don't understand actually compose around 95% of the total thing. Out of which around 72% is dark energy, 23% dark matter. About thermal, the radiational from the original time, the remnants are, this is only around 0.001%. So which actually was very strong at some point. Radiation also is a component of the universe. And at some point in the beginning of the universe, it was the major dominating component actually. Now matter and dark energy are more. So dark energy is 95% and this was 0.001, that's like 0.1% or something. And baryonic mass, which is what we are composed of. Baryons are electrons, neutrons, protons. This is around 4.5%, out of which is 0.2% is stars and intergalactic plasma. These are the rough numbers of what we see. White dwarfs contain so much. So these are the rough numbers of things that we see. This is the rough energy and matter content of the universe that we understand right now. This all is dependent on the standard model, though. You always have to assume some model. And that given that model, this is the correct thing. And why that model is correct or incorrect, we can go or not go later. We will make given time. So roughly, this is the energy content of the universe. And the last point that we will talk about a little bit, not the last point, one of the few last points is there is a phrase in Bible, there is a saying called, let there be light, and there was light. This is actually true in the universe. All the time we are recurring to the story of the cosmic microwave background. There is a reason, because towards the end, I'm also working on cosmic microwave background. So this will all tie up together. So this phrase, let there be light and there was light, is actually true. If you remember, I showed you some pictures, the first map of the universe, that there is Big Bang, then there is a period of inflation, and then there is something called the cosmic microwave background. So now what happens, this is our first visible light of the universe, and this is a very important thing. This is the picture that I showed you in the beginning. This cosmic microwave background, why it is important? Because before this, we don't have visible light, so the observations are difficult. And why is it so? Because you can imagine there is Big Bang and there is only energy in the beginning. At some point, energy condenses into elementary particles. Those elementary particles, all the while the universe is expanding. So all the energy, elementary expanding things also cool down. So energy has a chance to cool down. It condenses into elementary particles, E equal to mc squared, energy equivalent to mass. So now as things cool down even further, the elementary particles, they combine together to form protons, electrons. As things cool down further, the proton and electron, it combines to form a hydrogen atom. This is the first atom that we form in space. Now this reaction is irreversible though, meaning a photon which is sufficiently energetic, it can knock into a hydrogen atom and it can split apart the proton and electron. So in the beginning, when the universe is very hot, if it's created in the moment of Big Bang, it's very hot, then it's filled with very energetic photons. Radiation is very dominant at that phase, it's very energized. Then as long as photons are energized enough to split the atoms into constituent protons and electrons, the universe is opaque to radiation, meaning the free mean path of photon is very small because it's always colliding with plasma electrons and getting low. But the moment the energy of the photon crosses this 1 electron volt barrier, goes down below this is when it does not have enough energy to knock electron and proton out. This is when radiation photons become free for the first time in the universe. And after that, streaming very freely across the universe after that. This is when light separates for the matter for the first time in the universe. Till then, their history, their evolution is coupled. So this represents our first window into what happened in the very early universe, just after 300,000 years after Big Bang. This is actually a very early time. And the discovery of the cosmic microwave background is actually the clinching evidence for the Big Bang theory. Why? If you think of, so Big Bang means that it is an explosion. There is something exploding. You can equate it with a bomb explosion, but with a difference. The difference being that bomb is exploding in space, but Big Bang is the explosion of space itself. So it's much better to think of it, for example, a balloon surface. When you blow into a balloon, the surface of the balloon is expanding. It was the same thing, but it's expanding into three-dimensional space. Something similar can happen in 4D. But if there is a Big Bang, if the universe began in a hot, dense state, then one of the predictions was that you will see the remnants of this event in the universe. Why? Because imagine when there is a nuclear explosion, then you see this nuclear cloud. This cloud of explosion is what we are noticing as the radiation. Something similar would be there in the universe also, if there is a Big Bang. So around 1963, 67, there were these two guys, Penzias and Wilson. They got the Nobel Prize for discovering this. They were NASA engineers actually, and they were pointing their telescope in the sky somewhere, looking for something else, in fact. And they noticed that no matter what direction they point there, this was the telescope. This is almost the size of a living room. These are very big radio telescopes. So they noticed that no matter what direction they point their telescope in, there is a background noise that they detect and they cannot get rid of it somehow. And this is always a problem. So they spent 2-3 months trying to clean, like if you cannot explain something, you have to try to understand what is the source of the noise. So they literally disassembled everything and they looked at all their instruments and they reassembled, they put it back and everything the same. Eventually, at some point, they even climbed into the telescope and they saw that there was a huge pigeon colony, nest of pigeons, and it was full of pigeon poop. So they spent another 2-3 months cleaning that pigeon poop. And about a year of trying to figure out, they still don't figure out why is this background noise everywhere. And these are engineers, not scientists. But eventually they write a paper saying that we detect something at some temperature level around 2.7 Kelvin or something, and we have no idea what's going on. But then this is actually, they did not realize at the time, but they were actually detecting the cosmic microwave background. This is the universal thermal radiation left over from the time of Big Bang, which is present around us even now. And this was one of the predictions from Georges Lemaitre's theory that the universe had a beginning. If it had a beginning, then you would expect some sort of a relic radiation to be still left. And it's actually not very far away from us. If you remember these old television, about 1% of the signal on the noise in the television that we see at the time, this is coming from the CMB photons actually. This is the noise of the CMB photons. This is among at the radio waves right now. And so it is around us. If I hold my fingers like this, about 1 centimeter cube of my finger holding like this has around 400 photons from the time of Big Bang at the moment right now here. This is by far the most abundant species in the universe. So far, so that if we are looking at the universe in the visible spectrum, meaning Vidgyur, but if we could look in the microwave spectrum, the light of the Big Bang is so intense and so bright that all other lights will drown out, not the sunlight. You will not see anything else except the light of the Big Bang, if we could see in the microwave spectrum right now, actually. So it's all about how we can see and what we can see. And it is one of the most perfect black body. And this is not so important right now. One of the questions that we can also ask is that the question is the universe, how old is the universe? Is the universe infinitely old? This is called the Olbers paradox. In an infinitely old universe, if it is large enough and it is old enough, every line of sight, if you make a line of sight, if you look in any direction, you will catch a starlight. If that be the case, then eventually, if the universe is large enough, all the stars in the universe have had time to reach your eyes. Then the night sky should be infinitely, like it should be as bright as the sun. So why is it not happening there? Why is the night sky dark? One of the consequences is that the one explanation is that the universe cannot be infinitely old. This is the only explanation why night sky is dark. Otherwise, if it had infinitely enough time, every starlight will reach us eventually and large enough. So it will be very, this means that the universe must be finite. This is how one of the ways we think of the universe. Then we can ask the question of cosmic origin, if there are many universes or multiverses or not. The reason why we ask this question is this is actually very interesting. Now we have come to this point that we say that Big Bang, okay, Big Bang happened. We will not talk about what happened after Big Bang or before Big Bang. But even if we take Big Bang into account, there are a few problems that we have in the universe. One of those problems is the flatness problem, meaning why is the universe flat? We measure the curvature of the space-time and we measure it almost flat. It could have been positive, it could have been negative. Why is it almost flat? And flat is very good for us, but it should not have been. And if it is flat now, it should have been even flatter before. If that be the case, the second question is, if we look at the equations of electromagnetism, they are actually symmetric in charge and in magnetic field, but we only detect monopoles in electricity, meaning that electrons and protons can exist separately. Such a situation happening in magnetism would also indicate the existence of a north and a south pole separately. But from now what we find is that north and south pole always come together. If you cut a magnet into half, you still see north and south pole. This is the dipole term in magnetism. Where are the magnetic monopoles? We see that Maxwell's electromagnetic equation shows that electromagnetism is symmetric, but we only see protons, like electric charges can separately exist, but magnetic charges cannot. Why not? The third question that we ask is the horizon problem, and also problems that we can ask all these questions. Also, one of the questions that we asked before, why are physical laws exactly how the way they are? To answer some of these questions came a theory called the theory of inflation, which in my personal opinion is also science fiction, but science relies a lot on science fiction. What it said is, right after Big Bang, something that was of the size of around 10 to the power minus 35 meters, which is almost Planck scale. This is very small length, 1/1 and 35 zeros, becomes the size of a galaxy, which is 100,000 light years, meaning light takes 100,000 years to go from one end to the other. And this happens in about 10 to the power minus 27 seconds. So something really, really tiny becomes something really, really big in a very, very small time. And if this happens, we cannot again test if this is true or not. But this explains a lot of things after Big Bang. Before Big Bang, not, but at least Big Bang, the clinching evidence was this remnant light. This is how Big Bang trumped over steady state theory. And the problems in Big Bang, they are being solved by this inflationary theory, which may or may not be correct. We do not understand, but it at least solves some of the problems. But these are the things that we come today, that eventually, like some of the more observations we have, some of these theories are turning out to be not giving correct answers. The observations are not matching with theory. So we are in a space where things can, yeah, like we are in a very exciting time when we see that our understanding is not complete. We can see more and more. So one of the results of inflationary theory can be that the space can spontaneously go into an inflationary mode at multiple places. And this could naturally give rise to a multiverse, which would solve the question of fine-tuning about why are the certain numbers in our universe exactly the way they are, so that we are here to ask this question. If we had statistically infinitely many universes, those universes could have their own sets of laws, and then the problem is solved. So if we could find an evidence of any other universe, this is a big thing for this inflationary theory and this fine-tuning problem. Why is it like this? Then one of the questions we can ask is, are our brains sufficiently equipped? But we will not go into it because that's not my domain of thing. But my domain of thing is indeed whether one of the questions that we ask is, are there other civilizations out there? And one of the major endeavors of astronomy is to ask this question, are we alone in this universe or not? The answer is that we don't really know, but there are certain indications of many things. For example, water that we thought is only present on Earth seems to be, it's a ubiquitous present. On hindsight, though, we can imagine that it would be the case. Like water is ubiquitous across the solar system. It is in a lot of places. And there are also evidences of organic molecules in Saturn's moon, for example. And there are quite a lot of other indications. We have recently confirmed that there is water on Mars and moon, definitely. Saturn's Titan has water. So there could be things happening. But we still haven't had any evidence for extraterrestrial intelligence, not yet. Or that's yeah. This is something that we will not go into. But there are evidences of things happening, and there are many stars, many planets. A rough estimate of the number of stars in our galaxy is roughly the number of sand grains on our planet, on all the beaches, on all the river basins, on all these. So all the number of sand grains is the number of stars roughly in our galaxy. And the number of galaxies in the visible universe is again roughly the number of sand grains. So the possibilities are infinite. But why have we not been able to find anything? And these are different questions. The alien communication, extraterrestrial civilization. What would communication mean with them? Can we communicate with them? And if we communicate, what communication means? But these are things that I will not go into today. Then I come to a very small part. So this was the background of, like, this is a general popular level talk of what is the current state of the art of what we understand in the universe of what's going on. The second part is related to what I do, and it's data analysis, what we call topological data analysis. This is one of the recent developments in data analysis, and I was lucky enough to be working with a guy who is the inventor of these things. And somebody asked the question, Supro asked the question about machine learning, data analysis. These are all very interrelated. When you are doing machine learning, the moment there is data, and data is everywhere, it's ubiquitous. When we go into data, we are doing sort of a machine learning. But traditionally, then machine learning, the basic component of what machine learning is based on mathematical disciplines of probability and statistics. This is the core thing. And then being able to predict on something. Why I say probability? Probability gives you a power of prediction over something. You can see a pattern. You can see with this much chance I can do this. And and statistics, it gives you, again, like it gives you a pattern. You can see what things are going, and based on that, you can predict something. And these are important things in finance. It is important in every discipline about what's going on. So topological data analysis, it brings topology into data analysis. And topology is basically something we study. Topology is the study of shapes. You can go on to, for example, I'll show you a website. This, you should check out this. All of you, if you are interested in how TDA, topological data analysis, on how all these things are used in finance, for example, should look into iasd.com. This is one of my rather a teacher, not collaborator, teacher and collaborator both. He's a professor at Stanford. He started this company called IASD. Now he is not so much involved because he likes more to work on the things than be in the business side of things, but he started all these things. And here specifically, you should, if you're interested in what's going on, you should check out their knowledge center and their white paper, for example. They have something, you look at here, white paper. So white papers. So TDA and machine learning better together. What is like catching the unknown, cyber attacks. They have quite a few white papers, and they also have some examples on how they use it to detect financial crimes, for example. And there's a lot of things going on here. You can check on all these websites. There was also an article in Guardian about topological data analysis. If you say Guardian TDA, you will find this article basically. So these are state-of-the-art, very recent introduction into the area of data analysis. And I am interested in introducing these things in the analysis of cosmological data set. So for example, here is a paper that says how to predict the cosmological structure formation from machine learning. So all of these things, they are being very used. There is another paper where homological scaffolds of brain. This is a very interesting paper. Here they are. So they look at the functional network of the brain using topological methods, once when there is a test subject and once when the subject is on psilocybin. Psilocybin is the ingredient of magic mushroom and LSD. These are psychoactive, like these are psychedelic substances. And maybe I have a picture here. Come on. So on the left hand, if you see this picture on the left hand side, this is a normal brain, which is this shows the connection between various parts of the brain. On the right side is the brain connected on LSD, for example, or psilocybin. So there are very interesting things. With topology, you can study the shape, the connectivity of various objects, and these objects you have to define what they mean. And intuitively, what it means, you can have topological cycles and holes of various dimensions. A zero-dimensional hole is a gap between two connected objects. Immediately you can say, if we are talking about connected objects, then we can talk about clustering. And if we can talk about clustering, we can see how things group together. If you had, for example, stock market, you have 10 different kind of stocks, or 10,000, then you can see, like, do some of these stocks group together, for example? If they group together, how do they group together? In what dimension, what space? Space meaning, do they group together in daily fluctuation? Do they group together in price or price difference? Something, this is not my line, but these are the questions that you can ask. So these are concrete topological structures. A one-dimensional hole in space is something that you can walk through. But this in an arbitrary data set would just mean that there is no data over there. And if there is no data over there, why is there no data? Why is that group absent, for example? We can ask all these sort of questions. And then we can ask, how do these groups combine? So the idea is that you start with some functional landscape. This on the right-hand side, this image that's going on is the picture of the cosmic microwave background, where these are the temperature fluctuations and how things combine and join together. But the same thing you could do with stock market, price, or any other imaginable fields where you have some sort of a function, density, temperature, price, whatever you want to look at. These are general formalisms that you can adapt to various settings. And like I said, I am interested in the cosmic microwave background. I'm doing with the cosmological data set. And we look for, like, there is this Planck data set, Planck satellite that goes in the sky, looks at the CMB at different wavelengths. And the idea is to be able to confirm. So if we make a theory, there is a standard model of cosmology that's predicting something, that's saying something. And one of the things that it says is that the universe is isotropic and homogeneous. This is also the anthropomorphological principle, meaning it is the same for all the observers everywhere. And it's also Gaussian. But you can test all these theories by looking at the observations of cosmic microwave background and comparing with the simulations that you think your theory is. And long story short, that the observations are not matching the simulations, meaning, like, and it's not only me right now. There is all these numbers that you see around here in dark and black. This means that there is something really off between what we see on the map of the cosmos and what we understand from it, meaning that there is something else going on which we do not understand. And this is not only me at the moment. There is also, I think this is the end of my talk. But this, when I say this, there is also a lot of problems. So when we talk about this, is not only me that notices these things at the moment. When we look at the expansion rate of the universe, this is one of the most talked about topic at the moment. We define that the universe is expanding, but an expanding universe, when you look at when you measure the rate of expansion of the universe with the cosmic microwave background, which is the very early universe, you get one number for the expansion rate. When you measure the expansion with the current universe, with the objects in the current universe, the expansion rate is, hello?
Yeah, we can hear you.
Yeah, we can hear you.
Okay, okay.
We are eager to hear you, Pratyush.
Okay, no, I thought because I stopped sharing my screen, I got a little bit confused if something happened. But anyway, so like we noticed that the expansion rate of the universe is different at different time epochs. And our basic model says that the expansion rate of the universe is the same. This could mean 3 things. Either our satellites are wrong, where we are spending $1 billion to send it up, which and like one satellite could be wrong, but having multiple measurements and multiple measurements confirming the same kind of thing, it is not satellite measurement problem, at least over a period of few years. Then the more interesting alternative is that the universe is doing something more interesting and exciting that we don't understand. And the more measurements that we are getting, the more we are finding discrepancies in our understanding. And these are exciting times. Maybe there is a multiverse, maybe there are aliens. We don't know yet. And even if we know, we cannot be very sure and confirmed about it. Well, with that, I will end my talk. Thank you.
Thanks, Pratyush.
I will stop sharing my screen also, unless you have questions regarding some pictures of this talk. If not, then I stop sharing my screen.
There are some questions which I have. The first question, how are black holes actually found, and are there new planets forming?
There are planets forming all the time, yes. So like these questions, what was it? How are black holes formed, or how are black holes observed?
Observed or found.
So as we know, there is no direct evidence, because everything that goes into a black hole does not come out. I think this should be common knowledge. Even light cannot escape from black hole. So now we have direct, then what we do is a indirect observation. Like if we see a star going crazy somewhere, but we do not see anything around it, maybe then there is something, there is a mass that's influencing it. So stellar orbits, looking at things around the black hole circumferentially, is how we detect there is a black hole, what we call a black hole there. And what was the second one?
Second question is, what are your thoughts on the universe versus multi-universe debate? Is it possible that dark matter is gravitational effect of a parallel universe that we cannot perceive?
I will not go into no this if this is, we have to also disregard more normal sounding theories before we go into the parallel universe affecting our universe's matter content. If there were to be such a parallel universe, no, we have to disregard. Then first we have to understand what our theory of gravity is. Whenever we try to build up theories, we try to go off from the most logical explanation to the least possible, also verifiable. If we say it's another universe, at the moment we don't have a way of verifying it. So we make step. This is a hard business. It's a hard game. The question that you ask is a very good question for a party, but to answer this question is extremely hard if you want to be very honest. Then the way to say is like, first we have to try to understand what is gravity and what is dark matter. It could be not, everything is open. But first we have to understand deeply about what gravity is in that case, which we don't. So of course, all these questions are open. If there is a multiverse, it's quite possible that it's influencing our universe in some way. But we do not have an evidence of such a multiverse yet.
Thanks. Third question is, if Pratyush could please unpack black holes and supernovas for a pleb like me, and I'm sure or others too. That will be
So,
great.
I saw this question. There is a stellar life cycle. Let me look at this. I stopped sharing my screen. I will reshare my screen. Mm, okay. So this is a plebs version, which is also very informatic actually. This is the stellar life cycle, basically. What happens is, so it's all a cycle, like some stars burst and then there is a gas cloud and that contracts again and forms more stars. So in between what happens is that you can, depends like what, it all depends. It's a question of how massive an object is, what determines what can happen. So if it's a very low mass star, it will be a brown dwarf. It will not go any far after that. It will just become, it will not even form a star hot enough. Like Jupiter could have been a candidate for a brown dwarf if it was a little bit bigger. A little larger is low mass star, like are less than 8 times the mass of our sun. They have a certain way of evolution. Stars which are larger than 8 solar masses, they have another way of evolving into different stages. So less than 8 solar masses, it will go into a red giant definitely. After that, it depends on what's happening after that. If it's a binary white dwarf, it will, if it's in the companionship of a binary white dwarf, it will go into a type 1 supernova. This is what we were talking about, that if its companion is taking away its energy. If not, it will eventually explode singularly and it will form a planetary nebula, which will give rise to the second generation of stars and planets, basically. Actually, if you, by the way, our sun is not a first generation star, because you can think it actually took, it's at least a third generation star. 2 other stars have died in the vicinity of the solar system, is when we form our solar system and our elements, because the mass of sun, all the heavier elements in the universe are necessarily formed inside the core of a star, the star, and how much it can synthesize, what heavier elements it can synthesize with fusion, depends on the mass of the star, up to also the mass of iron. After iron, the energy required for fusion is more than the energy that comes out of fusion. So fusion cannot happen of higher elements. So stars can form up to iron after that fission and all of that. Then there are other elements, the other mechanisms of forming higher elements. But up to iron, heavier mass elements. But sun is not massive enough. Sun will die down after hydrogen and helium fusion because its mass is not sufficient enough to make it collapse further to ignite carbon and oxygen. But there are massive stars which have done this before. But the fact that we find in our solar system via carbon, there is all kind of heavier elements present here, means that we are the remnant of an older explosion, like something else died before us. We came into existence. So then there can be a nova or a white dwarf and black dwarf. Eventually, depending on the size, how big we are, if it's a supergiant more than 8 solar masses, it will form type 2 supernova where things explode very by itself because it's just too big to not explode. And then depending on if it is very massive, there is nothing left at all. But if it is less than 100 solar masses and greater than 40 solar masses, it will form a black hole. If it is less than 40 solar masses, it will form a neutron star and pulsar. So black hole is a very specific. So if it's it forms if it's less than 100 solar masses, but around greater than 40 solar masses. And when black hole, a star dies and forms a black hole. This is a very specific condition. But then there can be other kinds of black holes. There are primordial black holes, stellar black holes. Can be many kinds of black holes that form. But I hope this answers your question a little bit at least.
Okay, we have another question for Punyashi. Is the what was the temperature of space during Big Bang? Then does
During big, it's billions of degrees. We do not know very much, but it's very high, very, very billion. Or no, we know it actually. I don't know very much, but at the moment of Big Bang, it's billions and billions of degrees, very high. At the time of the cosmic microwave background, when light separates from matter, this is around 3000 degrees temperature. And right now, the ambient background temperature of the space is around 2.7 Kelvin. This is the temperature of the cosmic microwave background that we talked about. But before that, at the moment of Big Bang. So it has to be, depends on what, like we can think about the temperature in terms of the temperatures that we, for example, see at the particle accelerator. Because E equal to mc square, if the particle has condensed and before it has condensed, the energy must be higher than the particle E mc square. So everything was energy before, and electron volts, billions of electron volts. So the temperature was really high, very, very, very high, unimaginably high
The second
at
part
the
of that
moment of Big Bang.
the second part of that question is, does temperature have any effect for expansion of universe, or is it due to basic forces the universe has expanded? What are other factors for expansion of universe?
If we understand, so there are also big doubts. We understand though that the universe is expanding. Now the question is if it's accelerated expansion or if it's also a uniform expansion. Uniform expansion, this is, so I say this because there is a doubt, but some guy who got a Nobel Prize for discovering that the universe is accelerated expansion. Accelerated expansion means that there is a repulsive force acting somehow. Now, is this observation correct also or not? Then we can go into those questions. But if those are, all these things are correct, then like we can talk about the ambient temperature of the space. So which is the we are not talking about the temperature of the stars, for example. These have decoupled from the space expansion. You can think of something. So there is a constant fight between gravitation and this expansive force. But locally, things have decoupled from this universal expansion, or else our galaxy would not form, the stars would not form. So locally, things are actually like being able to overcome the spatial repulsive expansion. But on what scale they are being not able to is another question. And so the temperature is rather an outcome of, at the present time, let's say, when radiation pressure, temperature we associate with radiation. Radiation also has a pressure. So this is a very genuine, normal question actually. Is temperature the result or the byproduct, or is this the cause of the expansion? What we see, like at the beginning, radiation had something to do with expansion, but at the moment it is not strong enough to have that. Right now it's the dark energy. There are different components of the energy matter distribution in the universe which have taken over right now, and it's not the temperature at the moment. Temperature meaning radiation. It was there in the infant universe for some time, but at the moment not. So there has been radiation pressure. In fact, the fact that our sun is able to maintain this particular shape when it is because of radiation pressure. It is a very massive object and it has a tendency to collapse, but when it collapses also things become hot, and collapsing object becomes hotter. And in the case of sun, when it became hot enough so that its core could ignite nuclear fusion, that's when radiation pressure stabilized the inward collapse of the thing, and it's stable. So radiation does have pressure, but depending on the size of the scale of the universe, at the moment not. Radiation is not an important factor.
We have a question from Subhashish. Subhashish, you can unmute and ask yourself, please.
Maybe that's better.
Hi, thanks for this interesting session. So I was wondering, one of your slides, you showed that 95% of the universe is dark matter and energy, and about 5% is baryonic matter, which is responsible for the gravitational force, right? So
Not only, no, dark matter. When we say dark matter, there in that 95%, when we say matter, we call it matter because it has a gravitationally attractive thing. So in that 95% budget, I club them together because they are both in the dark sector. We do not know what they are. But one of them is attractive and the other is repulsive. Dark matter is also causing attractive. It's
okay, so we have that. Okay. Then it clarifies why there is still a balance between whether we don't know it is going to expand forever or will it contract at some point of time. Thank you.
It all depends also on the model of the universe, if it's correct. If the content of the universe is determined by the model that we use. And if that model is wrong at some level, then maybe some things are not correct, but which is also a debate at the moment. But everything has to be refined slowly, or else we understand everything and everything stops, but we clearly don't understand everything. So our understanding is lacking in many places. Yeah.
Okay, thanks.
You're welcome.
We have a question from Shubham. Shubham, you may like to ask it, please.
Hi, Pratyush. Can you hear me?
Yes.
Yes. So first of all, I absolutely loved your talk. I had this question about the Olbers paradox slide that you showed.
Mm-hmm.
So
Should I show this slide again, or?
yeah, if you could.
Yes.
Yes. So if I understand correctly, it says that every line of sight starting from where the observer is standing, so that should end up at a star, if the universe is infinite. But
you can have infinitely many stars also. Yeah.
Yes, but then if I understand, not all interstellar objects can emit photons, right? So it might also be that there are infinite number of stars, but then there are certain interstellar objects like planets or rocks or whatever that are blocking our line of sight.
This is the whole thing of infinite. It may be a planet, but eventually you will find something like, if there is an infinite universe, planet at least infinite universe would at least imply infinitely many objects.
Yes.
Infinity is a very strange concept.
Yes.
And the thing that you are asking, it's so like infinite. These are arguments against infinity. Like, give me any direction, and if I have infinitely many objects, I can say infinitely many stars also. Infinity lets you play around very easily with infinitely many things. If you say infinitely many planets, I would also say infinitely many stars, because those planets were around stars somehow, unless there is a rogue planet. So before going to planet, and these are very small objects, like, so eventually more or less all your line of sight should end up in an infinitely many star universe at a star somehow.
Could Einstein's general theory of relativity with light curving around certain objects, so that could also come into play here? Say
all of that comes into, but you are misunderstanding something. This is the play is between infinity. If it is infinity, it has all the time before us. It had infinite time before us for all the objects to send its light to us. Infinity is the very important word here.
Okay.
If it has all the time before us, if the universe is infinite in time before us and also in spatial extent, you have to appreciate the beauty of this word infinity. This is actually like, you don't understand it deeply yet. But if it is something like this, you will always have things going on. And on top of that, you can build Einstein's. Look, then Einstein's general relativity, it makes you detect more objects than you can directly see. So the number of objects will even become larger, because you're able to detect objects which you would not have been able to detect with something else in front of it. Because light is curving, it's a gravitational lens. So lensing is actually increasing the number of objects that you detect.
Okay. Yep.
This can only mean, if this is, then if the universe is infinite in space and time, our night sky should be as bright as the day sky. But if it is not, meaning that all the objects have not been able to send their light to us. So either and or, if there are not infinitely many objects, meaning there's not infinite in extent and time both.
Okay, I have another small question.
Okay, just a thing, 2 more questions, and then we need to wrap it up.
Sure.
And we can forward the rest of the questions to Pratyush. And Pratyush, I will send you the list, and you can answer them either through email or Zoom, whatever you prefer.
Okay.
I have a quick yes or no question, basically. So some years back, I read about this theory called Big Crunch. So does this theory still stand, or has it been like?
So there is something called the conformal universe. I did not want to, but this is a serious theory now. Big
Okay.
Bang and Big Crunch both are a part of the unending cycle of the universe, which we have been saying for a long time, Hindu cosmology.
Okay. Okay.
That like Brahma's one moment is 1 billion trillion. If all of the, I don't know, but these are natural questions, no? That
Yes.
if there is Big Bang, what is before Big Bang?
Uh-huh.
And if there is Big Bang, it started, it expanding. What is the end? It depends on the content of the universe. So when I showed that picture, when I said with a caveat that this is the fate of the universe that we understand after 100 trillion years, this is based on the standard model and what we understand, gravity, dark energy will go on expanding. But if our understanding is wrong, it could end it. So if our density estimate of the universe is wrong, if our energy content estimate, if our curvature estimate is wrong, all of these things can have a different value. They can change, all of it can change. And
Thank
all
you.
of these will have an effect.
Ronak, you can unmute yourself and ask your question, please. Ronak, can you hear us? Okay, Pratyush, in the lack of time, what Ronak had asked was, does dark matter and black hole have some sort of connection?
It could be. One of the candidates for dark matter is black holes. This is the things going on. And not only this, I mean, think about it. We can only we only see things that emit light. And all the invisible things, there could be a lot of undetected objects in the universe. And if there are primordial black holes formed, then this is even stronger. Like, so dark matter is all the unaccounted mass that we are not able to see. And black holes could be one of the candidates. Yes. Yeah.
Hey, Pratyush, I have a question. Can I just ask?
Yes,
Yes,
my
please.
guy.
Yeah, thanks, Pratyush. I think I completely enjoyed your talk. It was so
Thanks.
captivating.
I hope it was entertaining, at least. If
Yeah,
nothing
yeah,
else.
definitely. Hey, so
I
what
hope
are
it's motivating enough, Supro.
no, I mean that's fine. That's talk for the separate day, I guess. But then lovely. What are some of the active areas of research in cosmology which you might be involved in, or maybe your peers are involved in?
So cosmic microwave background, for example. And then the areas are how is structure forming, structure formation and evolution, galactic dynamics, star, like solar system, everything. It's a very vast area. You can look at the early universe, which is what I'm doing. I'm doing cosmology, so I'm broadly interested in how structures form and evolve in the universe. You can go smaller, look at galactic dynamics, for example, how there are so many different kinds of galaxies that we see: spiral galaxies, bar galaxies, disk galaxies, YR galaxies evolving like that. Then planets, like some of the major hot topics right now is for finding exoplanets, for example. And we see so many exoplanets. Then, of course, recently gravitational waves, like we detect gravitational waves that Einstein predicted 100 years back. That's also a very hot area of research. There's quite a lot of things going on.
So the advancement from the engineering and science actually help you guys to kind of do
Of
research.
course, of course. So it's like once you ask very deep, strong questions, there is no distinction between science or engineering or anything. Everything is a part of. For example, when I said in the beginning that cosmology is a useless thing that I'm telling you about, it is true and not true both. For example, the invention of CCD camera, it happened because of cosmology. All the medical imaging that you're doing, this is a direct outcome of cosmological imaging. Every photography thing that's happening, imagine if you were trying to do the photography of a black hole, making the picture of a black hole. This is at the extremes of your photography techniques. And when extreme becomes real world, then of course there is, so then medical imaging, CCD, there is a lot of things, then X-ray, all of these things, there is a direct thing going on, which may not be, so what we are studying sometimes may not be immediately beneficial. But it can have effects, and everything that we study is important. So yes, engineering is very important. Like science tells engineers to do this, like engineering is the next step. Like we cannot observe things unless we have good machines. You can make a theory, but you can only test your theory with good machines. And how do good machines come unless you have a strong engineering thing? So it's all a very collaborative work, not one. Like, this universe is too big to be for one discipline only. Everybody is, even art. Art is very important for understanding universe. Like the question, you can ask any question in this field. At least everybody's question is important. Whatever you can
Great.
ask. Sometimes you don't have answers, but questions are
Pratyush,
all.
one last question for the session, and it's like it was immensely enlightened. Uh, this is again an extension from Subhashish. One follow-up on the Obler's paradox. Does it assume that over time everything in the universe is uniformly distributed?
Yeah, this is one of the assumptions. And infinite, if it's yeah, sure. Yes. If it's clustered also, still you will. Yes, you have to have a uniform distribution also. You can ask the question yourself. If all these infinite objects are clustered in one place, what could happen?
Sure. Perhaps, Subhashish, hope that answers your question.
Does it?
Yes, it does. Thanks. But
So think
kind
about
of,
yourself that
Okay.
if there are infinitely many objects, then
Subhashish, I'm sorry. We need to cut it down now. Ritesh, over to you for the closing remarks. We have just 4 minutes left.
Thank you. The rest of the questions I will email Pratyush with the name so you can get in touch. First of all, Pratyush, thank you very much for this very interesting session. Some of us came to know new things, and it has
I
also.
never saw the chat box. I'm sorry. I see actually there is a lot of things going on here. My apologies. But I will.
No problem.
Pratyush, you can read that chat. It is all right from our heart to you.
Yeah. We have been trying to have this session for the last 2 months with all the plan and all thing, and it came out. Thanks, Pratyush. And thanks.
I'm glad to. I'm happy that you give me this ikigai for Prashant's word.
Thanks to all the audience for the participation and for the questions. And thanks to Rahul, Abhijit, Prashant for coordinating and make this happen. I have got few chats and messages that this session was very interesting, and I think we may like to have a follow-up or session 2 in the coming few months. Maybe we can take up a small topic.
Yes, so actually, if you were interested, I could give you more detail into smaller topics, but after some time, let others also do something before But this is a great initiative. I would also like to hear different people as well. So,
thank you. And for all the participants, we will upload this lecture on YouTube to our Praktani channel. So you may like to subscribe, and also you may like to tell your classmates or senior dadas or juniors that we have this Praktani Adda and all these sessions are being uploaded. And second, if you think that you can speak on an interesting topic which can be useful for the Vidyapit family or a society as a general, please feel to contact me or Rahul or Abhijit through email, messages, Facebook, WhatsApp, whatever works for you. That's all from me. If Pratyush, you want to say anything? That's over to you. Thank you.
Ritesh, I just wanted to add one line. I just want to add one line to Pratyush. It was a session, something we can summarize as "Abhi na jao chhod ke ye dil abhi bhada nahi."
That's very true.
I would actually, now I see in the side, but we can do it another day. We could all just have an adda again. But भाई दादा खाना नहीं खाया है, बोलते बोलते अब मर जाएंगे, पहले थोड़ा खाना जरूरी है.
चलो, on that note, I'll
have a breakfast.
फिर मिलेंगे थोड़ा और ज्ञान के साथ कि क्वेश्चन पूछने लायक अपने आप को बना ले, कि हम लोग चुप रहे, थोड़ा क्वेश्चन पूछने लायक अपने आप को बनाएंगे, तब तक खाना खा के फिर मिलेंगे.
This is one line where every question is valid, absolutely. क्योंकि जो सीखने हो उसको भी नहीं पता है, हम लोगों को कुछ नहीं पता है, जैसे जैसे जान रहे और नहीं पता है. So everything is open here, very much. There is no stupid question at all. Especially in this, if you think about the universe, all of us are equipped to think, ask questions. Answer का किसी को पता नहीं है. सवाल हम लोग सब पूछ सकते हैं.
चलो प्रत्युष तुम्हारे लिए लास्ट क्वेश्चन है फ्रॉम अभिषेक एंड देन वी विल जस्ट क्लोज दिस. What secret does the masterpiece have about the universe?
What? Say again.
What secret does the masterpiece have about the universe?
Yeah. I will invite you to come and join, and then we will show the secret. Otherwise, I cannot speak.
Great. Thank you, Pratyush. Thank you, everyone, for joining us.
Thank you very much for
wrap, and we shall come back again with the new session very soon. Thank you. Thank you very much.
Thank you.
Wow, there is a lot of. Okay, I'm थोड़ा खाने जाते हैं and see you guys.